That stuff is
So, like, as long as the angle.
Pleasure today to host as our SICRM colloquial speaker Jiun-Haw Chu. Jiun-Haw is currently an assistant professor at the University of Washington. He graduated from National Chiao University with a bachelor in electrical engineering in 2004, and then went on to pursue graduate studies at Stanford, working with Ian Fisher and pioneering, among other things, some of the techniques that he's going to talk about today, specifically how to use in-situ strain to tune the properties of quantum matter. Then he moved on to postdocs at Berkeley and then back again at Stanford, and since 2016 he's a professor at the University of Washington. He's won every possible award since then, including the Air Force Young Investigator Award in 2017. Then he became a Material Synthesis Fellow, Moore Fellow. And last year he got the Sloan and Packard Fellowship, and this year he received the EKs, which is the Early Career Award for Scientists and Engineers. So it used to be the PKs, but without the P now. So today he's going to talk about topological materials and how strain can be used in this specific system to induce a topological transition from a weak topological insulator to a strong topological insulator. So please welcome Jiun-Haw and enjoy his talk.
Thank you, Ricardo, for the very generous introduction. Right, so yeah, I guess as Ricardo said, I'll be focusing on this topological material, ZrTe5. Although initially I was, when I was sending the talk title, I was planning to talk about both topological phase transition and quantum phase transition. And quantum phase transition is related to a superconductor metal transition in an iron-based superconductor induced by strain. But today's talk will be mostly focusing on ZrTe5, and then yeah, if you want to know more about the iron-based superconductors, I will be happy to discuss with you offline. Now, we found a series of very interesting behavior in zirconium telluride, and then one of the reasons is that this material is highly confused. And what do you mean by it is a confused material? So if you Google search ZrTe5, and then on the papers you can find, you can find a scatter of different papers with title claiming that it is a strong topological insulator, it is a Dirac semimetal, gapless, it is a weak topological insulator. So it looks like this material is very confused. It doesn't know what it is. It doesn't know what the ground state is. But what I'm trying to convince you today is that it is not confused. It is just critical. It is a so-called topological critical material. It is located at this vicinity of this critical point of this universal topological phase diagram that separates strong topological insulator, weak topological insulator, and Weyl semi-metal phase. So it's very close to this, and that allows us to use uniaxial strain to transform the material's ground state from one kind of topological phase to the other, as well as Dirac semi-metal phase. And also because it is very close to this critical point, the ball band structure behaves just like a three-dimensional analog of graphene. And therefore, just like graphene, when you go to very high magnetic field and then with very high mobility, you see a bunch of very weird transport behavior that I'm also going to discuss with you today. So of course, all this work is not really done by myself. It's really done by my students and my collaborators. So Josh March is one of my first students. He's wonderful and smiling here in this photo. He has driven most of the work in zirconium telluride. And then we have some theory support from Anton and Drive, the theorists local in the UW, as well as some DFT calculations from my friend Chen in the University of Alabama, Birmingham. And then, of course, we also cannot do this work without the funding from various agencies. Okay, so what I'm going to do with this talk is that I'm going to start with an overview of some of the things you're very familiar with, the topological state of matter, just to set the stage, and then try to introduce ZrTe5 as how, in the context of different kind of topological state of matter, why it is topological critical materials. And then I will try to tell you about our results of strength tuning this material and how, from the transport measurements as function of strength, we conclude that we have achieved a topological phase transition. And finally, I'm going to talk about some very weird transport behavior beyond the quantum limit of this bulk material. So start with the introduction of topological phases. So of course, the field of topological phases start with the quantum Hall effect. You have two-dimensional electron gas applying high magnetic field. You see very precise quantizations of your Hall conductivity in the equal to integer multiplying in square of h. And this is so precise that you can actually use that to determine the fundamental constants. And this is really coming from the topology by the groundbreaking work of Fowlers and the others, which was being highlighted in the 2016 Nobel Prize, that this kind of quantization is coming from the fact that when you're measuring the Hall resistance of this material, you're measuring a topological invariant. You're basically measuring the integration of the Berry curvature of the system, and then therefore it will give you the so-called Chern number, and then it should be independent of the detail of the system. It's just a global property of the system, and then therefore you lead to this quantization of Hall conductance. Now, when you observe quantum Hall effect, you need to apply a large magnetic field. So people thought about ways to see the same effect in zero field, and then the very important insight is coming from this very important paper by Charlie Kent and Eugene Milley on proposing a quantum spin Hall effect in graphene. So the idea of quantum spin Hall effect is quite simple. You just create two copies of quantum Hall effect, one spin up, one spin down, and then you superimpose of each other. And then therefore, the whole system is time reversal invariant. And instead of the edge states that is going one direction, now you have a helical edge state that with the spin up going one direction, spin down going the other direction. And the two-dimensional bulk is still insulating. Now, the first experimental realization is from the mercury telluride quantum well, but it's only after 10 years that people found a natural ground crystal and exfoliated down to monolayer that in a WT tube, you can also observe the same effect in 2D van der Waals crystals. And this was done by my colleague David Cobden, seeing the edge state transport when the crystal is thinning down to monolayer. So just like graphene, you can also define a topological invariant in this system. And so now the way to describe a topological invariant is a Z2 topological invariant. So what you do is that you look for this time reversal invariant point in your momentum space, and then you calculate the property of the occupied wave functions in those time reversal invariant point. And if it's an inversion symmetric system, then it's really just calculating the parity eigenvalues of these occupied states and then doing some multiplications. And then there you can find out the topological invariant. If it's 1, then this is a topological insulator. If it's 0, then it's a trivial 2D insulator. So now an interesting question is what happens when you extend this idea to 3 dimension? So when you stack a lot of quantum spin Hall insulator to 3 dimension, then one very natural expectation is that you just have a thicker quantum spin Hall insulating state, meaning that instead of edge states, now you have a crystal with a 3D insulating bulk, but you also have a side surface. Have this helical surface states on the side of your crystals. Now, this is indeed what happens if your quantum spin Hall insulator are loosely coupled, and therefore there's less hybridization along the z direction. But if you have more hybridization and have one more band inversion, then you can even reach to a regime called strong topological insulator, where all the surfaces have protected surface states. So, and that can actually be formally defined by, again, the same kind of topological invariant, but now with more time reversal invariant points in the Brillouin zone. So you have more topological indices, and then therefore you can define the strong topological indices and weak topological indices. So when you have non-zero strong topological indices, it's a strong topological insulator. And then when you have 0 strong topological insulator indices, but non-zero weak topological insulator indices, then you have a weak topological insulator. So weak topological insulator can loosely thinking as a 3D version of a quantum spin Hall, 2D quantum spin Hall insulator. And again, here you also have a signature here, which is you have some protected states at the boundary of the system, which is a surface state, like the RPS measurements here showing the Dirac surface states here on some typical 3-dimensional topological insulator. Okay, so you have different kinds of topological indices, but to switch between topological indices, you always need to change the property, the eigenvalue of your occupied wave function. So what it means is that you have to really switch the states of these in your energy bands at this point. So that means that the bandgap has to close and then reopen again when you switch from one topological indices to the other. So in the vicinity of a phase transition from one topological insulator to another topological insulator, let's say from strong to weak, or strong to trivial, or weak to trivial, then close to the band inversion point, or time reversal invariant point, you have the following scenario. The band will look like a massless Dirac dispersion when the band exactly touch, and then it will look like a massive Dirac dispersion on either side of the phase boundary. And then the sign of a mass is basically determining you whether you're on this side or that side of the topological phase boundary. So this massless Dirac point, so in some sense, when you're getting very close here, then the bulk itself also becomes interesting because now you have a very beautiful Dirac dispersion that can displace all sorts of interesting physics. But on the same time, this Dirac point is also not stable because this is only happens when you tuning right at the critical point or the phase boundary. Any kind of perturbation will drive you away from the phase boundary, then the Dirac point is gap. So if you can apply in some other symmetry breaking field, like magnetic fields or inversion symmetry breaking field, like electric fields, or just from the crystal structure that break the inversion symmetry, then you can break the degeneracy of the fourfold Dirac points. Right? So you have fourfold degeneracy here, double degeneracy on the conduction band and double degeneracy on the valence band. So you break it into two-fold degenerate Weyl points. So you end up with this universal topological phase diagram where on one side you have one kind of topological insulator, on the other side you have the other topological insulator. And the vertical axis is some symmetry breaking field, inversion symmetry breaking field, or time reversal symmetry breaking field that leads you to a Weyl semimetal phase that is stabilized by the strength of the symmetry breaking phase.
Is there something you can do to drive it to a trivial phase, totally trivial phase? Band insulator?
Yes, you can. Yeah. So it's just that in this particular case, I'm going to talk about, you're very close to this, but the same phase diagram apply to other kind of switching, strong to trivial or weak to trivial. Yeah. Yes.
Like for example, within you're going to square 5.
Oh, it's probably difficult. I mean, it's quite far away from the trivial insulator phase. Yeah.
Could you explain again what the difference between strong and weak is with topological?
So strong, right? So strong is just phenomenologically strong. You have a Dirac surface state for all the surface. It doesn't matter which crystal surface you have. But weak is more like a stacking of 2D quantum spin Hall insulator, right? So when you have stacking of 2D quantum spin Hall insulator, then you can think of the edge states becoming the side surface of the crystal. So now in this case, you only have certain crystal surface you only have surface state on those particular crystal surfaces. So weak topological insulator, only particular surface, particular crystal facet has a surface state, but strong have surface state everywhere, and trivial doesn't have surface state anywhere.
The only difference is the hybridization between layers.
So yeah, for one particular model, yes, depends on how strong the z direction is hybridized, and you can have different kind of topological insulator. Right. Okay, so this is a general phase diagram. I mean, one particular thing about this Dirac dispersion and Weyl Semimetal is that there's actually some transport signature that you can see from measuring the bulk magnetotransport, so which is the so-called chiral anomaly. So the idea of chiral anomaly is that if you have two Weyl points, they could be in the same K space or separated in K space. If they're in the same K space, then they're just Dirac Semimetal. If they're separated in K space, then they are the Weyl Semimetal. Now, when you apply magnetic field and then applying electric field in the same direction, then you can pump the charge from one Weyl point to the other. And what you actually see experimentally is that you'll see the resistance will drop as you apply magnetic field parallel to your current direction. And this is because now you introduce some additional chiral current along this field direction, and therefore the overall resistance drop. Now, the initial theory really requires that this whole thing to be intersecting exactly at Weyl points. But there is some later work by my colleague Boris Spivak and then some in Chicago. They figure out that even in the semi-classical regime, when you have Fermi level far away from Dirac Weyl points, and then you can see the same effect, and you can explain this in terms of Berry curvature. Now, although this measurement itself is quite tricky, it has been shown by Fuanon that some of the negative magnetoresistance you measure can just come in from some geometric effect of how you put the contacts and how the currents are jetting in the crystal. So there's some controversy, and then I'm going to coming back to this type of measurement when later on when I talk about stream. Okay, so how do we understand zirconium telluride with all the things I have introduced? So zirconium telluride is a van der Waals layer material. So it's a quasi one-dimensional. You can think of it as a quasi one-dimensional material. You have some zirconium tellurium chain. They bond together and then forming a 2D layer. And then this 2D layer weakly coupled through a van der Waals force, forming a three-dimensional crystals. So it was being studied in the early 80s, and then people thought there was a CDW, but later on they kind of actually found evidence of CDW. But more recently, there's a very important theory paper suggesting that the monolayer of this guy is actually a quantum spin Hall insulator, and then with a quantum spin Hall gap as large as 100 millielectron volts. And there's a lot of work trying to prove that it's like 2D quantum spin Hall insulator, and it's still not robustly proven yet. But its three-dimensional form also quite interesting because it comes back to the same question that I asked early on, which is what happens when you stack a lot of quantum spin Hall insulators together. But in this initial paper, immediately they found out that this question is quite tricky because when they do the calculations, they can use a experimental lattice constant or use a relaxed lattice constant in the DFT calculation. And then for each case, they found a different answer. So for one case, they get a 3D topological insulator with this topological indices. And then for the other case, then they get other topological indices, and then it's corresponding to a weak topological insulator. So therefore, this is why you have so many confusing experimental results. And then one of the difficulties is that when you're getting very close to this critical, so this is basically what happens. This is very close to this critical point. It could be here, it could be there, it could be there, and then most likely it probably depends on how you grow the material, how you glue down the material, how you strand the materials. Yeah, that's a question here.
So can you just explain more what this axis is that we're moving along? So my intuition should be that it should be strain along the Z direction to weakly couple or strongly couple the layers. Is that the right intuition of what this axis is?
That's one possibility to tune this axis.
But in the last slide, you said just the lattice parameters were 2% different. Like, is that in all crystal directions?
Right. So I'll come back to that. Yeah. So actually, it really depends on how you change the lattice constant, and then there is actually a sweet spot to most effectively tuning. Okay. So the short answer is that all the lattice constant change can either isotropically or uniaxially or will eventually lead to this. But each way has different efficiency. So some of them is more effective, some of them is less. Yeah, go ahead.
So is it understood at zero strain? What is the electronic constant? Is it like TI? Is it like
There's more. I think there's more paper favoring weak TI, but yeah. Again, I think one of the difficulties is that now you have a very small gap bulk electronic structure, which looks like Dirac dispersion. And then you're looking for another two-dimensional Dirac dispersion on top of this Dirac dispersion. And then this bulk Dirac dispersion is also quite two-dimensional because it's a layer structure. So okay, different group report differently. There are STM saying 80 electron volts, and then 80, and then there are RPES generally, for example, like ZX reporting something like 18 to 20. And then there are magneto-optics saying this is about 10. And then for our measurements, our estimate is between 10 to 20. Yeah.
You know, so if like ZX's microwave-impedance matching, or this is measurement where you can like visualize edge modes, like in WT2, should you be able to see those kind of edge modes when it's in the weak topological insulator?
If the bulk is insulating enough, right? But that's the problem. Yeah. Yeah, it's possible. Yeah, I mean, if you can thin it down to a very thin layer and then make the bulk insulating enough. Yeah.
But that wouldn't distinguish between. Oh no, that would distinguish between a strong TI and a weak TI.
Right. So supposedly, yeah, you'll see a different conduction pattern. Yeah. That's something that's possible. Yeah. Okay. So I'm going to tell you about how we use strain to go across that topological critical point. So yes, as I said, there's immediately people realize that the lattice constant is the key to kind of changing the band structure of this material. So there was a calculation based on this paper saying that, okay, you can tune from one phase to the other by isotropically changing the lattice constant. So negative corresponding to pressure, and then positive corresponding to negative pressure, and then their conclusion is that the ground state is in the strong topological insulator regime, and then you have to applying 2-point-something% negative pressure to go across the topological phase boundary. So yeah, so first of all, this is a large strain, by the way, 2.7%, and then also it's negative isotropically. There's no way you can do that experimentally. So, but there are ways you can do both positive and negative strain, which is applying a uniaxial strain. So that's why we're using this device, which was first introduced by Cliff Hicks et al. And then the idea is really using 3 piezo stacks that amplify the amount of movements of this 2 simple holding stage, that you glue the crystal across this gap. And then by controlling the motion of this and that independently by these piezo stacks, you can generating strain of the order of 1 to 2%. Right, so this is an actual picture. Right, so we bought some from the company that was started off by Cliff Hicks, but we also custom made this so that it can fit onto different kind of simple environment. And then just as a side, we use the same device to enhance the nematic order in the iron-based superconductor and then induce a superconductor to metal transitions with a strain. And then, yeah, as I said, I'll be happy to discuss with you offline if you're interested. Now, so this is not isotropic pressure, right? So you're actually pulling the crystal along one direction. And then for natural material, when you do that, you'll expect the contraction when you're pulling along one direction for the contraction along the other direction. And then for this particular material, it has a Poisson ratio about 1 to 4. So when you're pulling along, let's say A lattice constant, you're shrinking along the C lattice constant with only 25%.
It's kind of hard to see the crystal. It's a little like narrow piece.
Right. The crystal is less than 100 micron wide, and then this is 2 centimeters. So yeah, it's hard to see in this picture.
The contacts are made in some very conventional ways.
Yes. Yeah. Sort of yeah. Patience, steady hand. Yeah. You know. Yeah. No coffee. Yeah. So for this, so for ZrTes, we're lucky because the crystal naturally grown into a thin needle, and that's the ideal shape you need for this type of measurement. The thinner and then the larger the aspect ratio will give you more uniform strength for this uniaxial pulling. Yeah, but let's say for another technique you can use is directly gluing the prism on the side of the diazoostat. For there, you actually want the very square-like sample to get a full transmission for each direction. Okay, so the previous calculation I showed you was calculating the band structure as a function of isotropic expansion and contraction. So we asked our collaborator to calculate the band gap as a function of A lattice constant strength and then C lattice constant strength. So, and then it turns out that you see this response, the band gap actually has a very anisotropic response to the strength. So the black corresponding to 0 gap and then the white corresponding to maximum gap around 70 millielectron volts. So you can see that there's a valley here corresponding to 0 gap, also corresponding to the topological phase boundary between strong and weak. So you get the most efficient way to go across the phase boundary is extending A lattice constant and then contracting C lattice constant. But whereas if you go for the isotropic expansion or compression, you're basically going parallel to the valley. So that's why you need a very large amount of strength for that direction to go across the boundary. So the gray line, the gray arrow corresponding to the actual Poisson ratio we apply. It's not the most efficient, but it's sufficiently efficient that we actually see some signature of topological phase transition. And this is what the band structure look like on each side. So you really have some Dirac dispersion close to the phase transition. Yes?
Okay, but to interpret, you're just pulling the layers apart. Right? That's what this diagram.
Pulling the...
Up to the left, you're pulling the layers apart, right? See, the z-axis is getting longer than the z-axis.
No, actually, it turns out that it's not simply controlled by the z direction. So the band inversion of this material actually controlled a lot by the hopping between the chain as well. So
it's increasing with c decreases, right?
it's right, increase and then decrease.
Okay, so we're increasing the distance and we're improving the hopping by compacting.
So right, so you're decreasing both the interlayer constants and then the intralayer. Yeah. So yeah, there are some I actually cannot answer you exactly how which orbital is moving up or down to result in, but the actual DFT calculation is showing that this is the best way to invert the bands. Let's go ahead.
Might not be helpful, but did you also think about like chemical pressure, doping, something? I mean, perhaps that would move you along the isotropic direction, so that wouldn't help. But
right.
Because that wouldn't seem to be so hard. You put half in or something.
Right. Yeah, we thought about that.
It just makes it disordered.
You also introduce more carrier, and then it turns out that the effect what we're trying to see, actually, you see the biggest effect with the less amount carrier, closer to the band edge. Right. So let's talk about what we expect to see in transport when you're going across this topological phase transition. So in reality, you always have some finite carrier. So your Fermi level is not in the gap or in the Dirac point. I mean, if you're really in the gap, then you probably will see some insulator to semi-metal to insulator transition, plus some effect of surface state. But in reality, with this small gap semiconductor, you always have some ionized impurity, and then therefore with some residual carrier density. So our estimate of the Fermi level is somewhere around here, like 10 million volts or less. Now, so what you are seeing is the transport property of some bulk, massive or massless Dirac fermion, and then the mass is modulating as a function of strain. And so what you will expect is that the resistance will go down when you are going to a massless Dirac state and then going back up again. In addition, they should depend on the mass in a very specific way, because the transport, your mass could change sign, right, from positive to negative across this topological phase transition, but your resistance shouldn't depend on the sign of the mass. So therefore, the lowest expansion is the quadratic expansion. So if you can tune the mass linearly across the topological phase transition, you should expect a quadratic dependence of the resistance as a function of strain. And this is indeed what we see as a function of resistance, as a function of strain, the resistance change from has about 20 or 10% change with just less than 0.1% change of strain. So that's actually a very huge amount of change of resistance with such a small amount of strain. And then, but most strikingly is this non-monotonic dependence. You just don't expect that in ordinary semiconductor. In ordinary semiconductor, you sometimes will get like 100-fold enhancement of your change of resistance over strain, but you always expect linear response. So this nonlinear response is really telling you something singular happening in the electronic structure. And the most natural explanation is this: you're switching the mass from positive.
So how much is the distribution for this epsilon min? I mean, most of the crystals have very similar minimum epsilon you have to apply, or it can be very different.
Right. It actually depends more on how you glue the crystal and how it cool down. Yeah. And then in fact, we try to track the intrinsic epsilon min, but usually you lost track around 40 to 50 Kelvin. Somehow, you just have some thermal expansion strain that you just cannot compensate during that.
How about the coefficient for this quadratic dependence? Do you think that's also intrinsic?
Extreme. Yeah, exactly. So no, it actually directly tells you what your Fermi energy is, because right, this delta rho over rho is a dimensionless quantity, and then so it should depend on gap quadratically, but the gap should be normalized by another energy scale, and then the only energy scale here is Fermi energy. So, and then this is kind of making sense, right? The smaller the Fermi energy, you should get a larger response.
Can you check that with looking at the quantum limit?
Right. So for this set of samples, we don't see quantum oscillation, so we cannot directly check that. We can check with Hall coefficient, and then that match. The Fermi energy we extract as well for A and BV, and then also match with the literature and then all that. So it's a very nice way to actually also to independently kind of get to make things checks. Another way is that since the Fermi energy is very small, so you can increase temperature, then very quickly you're in a region where the thermal energy is above the Fermi energy, right? So you should expect some crossover from the Fermi energy quantum degenerate regime to a thermal excited regime. So therefore, we track this quadratic dependence as a function of temperature, and then you check the coefficient, you measure the coefficient as a function of temperature, and then you see this very non-monotonic temperature dependence, and it first goes down, and then going back up, and then going back down. So initially, we were a bit puzzled, and they're all consistently showing this behavior. But later on, when you actually do the Boltzmann transport calculation, it actually makes sense. At the very beginning, you kind of dominated your carrier density is fixed, right? You're in a quantum degenerate regime where the carrier density is controlled by Fermi energy, and when you're changing the mass, you're just changing the property of the quasi-particles near the Fermi energy. And then as you increase temperature, the Fermi energy is a bit blurred, so therefore you kind of have a decrease of this response. But as your as you go to higher temperature, then the thermally excited carrier become comparable to the number of carriers in the Fermi energy. So therefore, you have another mechanism to give you a strong strain response, which is the number of carrier excited across this conduction band and valence bands will be strongly modulated by strain. And then eventually, as you go into very high temperature, then you have a very broad smearing, and therefore your temperature scale is much larger than the mass energy scale you can modulate, and then therefore the system doesn't care about that anymore, and therefore you have a decrease, m/t² decrease. And yeah, so we do some quick Boltzmann calculation. On the right-hand side is the calculation with different carrier density. We see some some nice qualitative dependence agreement between the experiment and theory. Okay, so this is all zero field measurements. So remember that it was also the chiral anomaly associated with the Dirac semimetal. And people did observe chiral anomaly in or longitudinal negative magnetoresistance in this set of crystals. And since this material is likely gap, then how does it happen? So I won't go into the detailed theory, but there's a theory work done by my colleague Anton and Boris Spivak. They basically prove that in a semi-classical regime, the same kind of physics or same kind of phenomenon will still apply, and then therefore you'll still observe the same kind of negative longitudinal magnetoresistance, provided that if Fermi energy is large compared to gap. And then this is kind of expected, since when your Fermi energy is away from a gap, it shouldn't be sensitive to what happened down there. And of course, but when the gap increases, eventually this effect will disappear, and then the degree of weakening should depend on the ratio between mass and Fermi energy as well. So we have also done the same longitudinal negative magnetoresistance measurement. We observe the longitudinal negative magnetoresistance measurement. And then what is even better is that we actually see very strong modulations of longitudinal negative magnetoresistance. So the gray curve corresponding to when the resistance is sitting at the minimum, that's at the boundary where it's in the gapless state. And the blue curve corresponding to going further to the strong topological insulator phase, and then the red curve corresponding to going further into the weak topological insulator. So you can see that when you're stranding away from the critical strand, you always get a weaker, a more gradual decrease of magnetoresistance. So this confirms that you actually really opens a gap and then suppress this chiral anomaly. And yes, go ahead.
Strong and weak in this case, is there any signature in this particular longitudinal resistance data that's transition, or is it just effective on the negative positive stream?
So right, so we can independently determine that from just the zero field resistance, one side of the minimum. But we think we probably see some signature that distinguish between strong and weak that still under investigation. But if you look at this above 3 Tesla, 3 to 5 Tesla, so here the strong, you just see the magnetoresistance keep decreasing. But for the weak, it seems to be you have an upturn. That also depends on how much strand states you have. So there's actually a theory talking about how the longitudinal magnetoresistance could show some anomaly in the quantum limit in a topological insulator. So because the lambda level of topological insulator behave differently from the ordinary insulator, the last lambda level of topological insulator will actually have an opposite energy dependence as the trivial insulator. So if you're in the quantum limit, and then when the field is enough to kind of make the last lambda level cross, then you'll see some features and then that will depend on which kind of topology states you are, and then that could explain this, but you need finer measurements to resolve that. Yes.
Wouldn't that also just be a different density in the odds of the house?
So for this, we never see any Semimetal dehas. Yeah, and then according to that carrier density, you see that in some higher carrier density sample, which you measure from the Hall effect has much higher carrier density than this. So if you just infer from the carrier density, the quantum limit should be around 0.5 or 1. Right, so you're already in the last lambda level. Yeah.
Why is it that you're saying the mobility is not good enough to see it in both fields?
Right, so I think you already reached the quantum limit before omega c tau is large enough. Yeah, I think that's what happened. Yeah. So this is just some quantitative fitting of the magnetoconductance. So So now you have a positive magnetoconductance, and then from the B square dependence, you can extract a chirality or helicity relaxation rate, which in theory should diverge as you getting close to gap equal to 0 case, and then so this kind of fitting also kind of match the picture. Yeah, the last thing I want to talk about on the strain stuff is that, so we do this experiment by gluing the strain on a piezo stack. So the piezo stack contract along this direction and then expand along this direction. So when you glue a thin crystal, for this kind of crystal, you're experiencing a thermal contraction from the substrate when you cool down. And then for this crystal, you'll get a tensile thermal expansion when you cool down. And then you can apply voltage on the piezo stack and locally varying the amount of thermal strain. And then just prove that when you glue in this crystal on this different way, then you'll get an opposite slope, the opposite linear slope corresponding to these two sides of topological phase transition. So essentially, you can think of when you cool down, then the red crystal and the blue crystal are now in a different topological insulating phase. And that might be the reason why people are observing different behavior in different measurements. Okay, so right, so the quantum limit. Okay, yeah. Yes.
There could be any difference between people who are using like surface probes and bulk probes, in terms of what phase they're identifying?
Well, the bulk probe, they cannot determine which.
Well,
Well, no, I mean, it's kind of indirect, right? Yeah, but.
Well, then let me say, so do you think there's any chance that people who are looking at the surface, with everything you've said about the material, the surfaces can be different. Of course, there could be some band bending, but I don't know, maybe even some relaxation at the surface or something like that. Do you think that could be?
Yeah, that I'm not sure. Yeah, I haven't think about along that direction. Okay, so right, quantum limit. So to reach a quantum limit, you have to reduce the carrier density, and this material is very sensitive to how you grow it. So for example, like this blue curve corresponding to a crystal grown by chemical vapor transport, and then it has a maximum peak in the R-resistivity around 150 Kelvin, and then it turns out that this peak corresponding to an N-type to P-type to N-type transition. So now the crystal is N-type at low temperature with a carrier density about 10 to the 17. But if you grow the crystal by the flux method, then you never see the peak, or you can say that peak is around 0 temperature, and the material is always P-type. And the carrier density is much reduced to 10 to the 15. So my student did a bunch of crystal growth and then managed to reduce the carrier density to an extremely low level. And then, so these blue, this is carrier density 10 to the 15 to 10 to the 20. This is mobility. So trying different way, arc melting the zirconium, and then different crucibles, and then eventually reach into a region where you have very high mobility, about a million centimeter square per volt per second, and then with a very low carrier density, below 10 to the 15. So you're really pushing close to the your Fermi energy close to the Dirac point. And you can also kind of infer where the quantum limit is by measuring different amount of carrier density, right? So for this material, this is showing for the green crystals, you have a peak at a finite temperature, and then you can see the SDH oscillations, and then with a periodicity about 1 Tesla. And then for the blue crystal, you have a lower peak, and you can see the SDH oscillation with a periodicity about 0.5 Tesla. And now for the black crystal, it obviously has much lower carrier density, and then you don't even see quantum oscillation anymore. So here, this is a resistant plot in log B, right? So you start to see some very weird behavior in the ultra quantum limit where the magnetoresistance actually oscillate as a function of log B rather than 1 over B. Yes?
Is that just carrier scattering, or is that also carrier impurity scattering?
Okay, we didn't distinguish these two. Just do a very simple Hall resistance, and then you need arc melting the zirconium, and then to purify, and then and then you also need to choose the right container. I forgot, it's either crucibles or quartz tube. Yeah, that also matters. Yeah, and then also there's a few steps of annealing the zirconium tellurium, and then or during this cycle in between formation temperature.
Oh yeah, we did it.
Yeah. So, okay. So now we have a ultra low carrier density, ultra high mobility, and then we measure the angle dependence on magnetic resistance. So just to define the geometry, you're running the current along the A direction, along the Chen direction, and then you're rotating the magnetic field always perpendicular current. So from out of plane, out of layer to within the layers. And with a weak field, and let's say 100 Kelvin, you see some large, but still rather conventional magnetic resistance, two-fold oscillation as a function of angle, right? So you have larger magnetic resistance for field out of plane because your mobility is higher in plane, and lighter effective mass in plane, and then when you rotate it in a field in plane, then you have a less magnetic resistance because the effective mass is higher for the interlayer direction. So you have this two-fold behavior. But if you go down to very low temperature, not very low, 2 Kelvin, and then going to high enough field, let's say 14 Tesla, then you see this very distinct peaks emerge at these specific angles, right? And then, this is quite surprising because you're already surpassing the quantum limit. You shouldn't expect, there's just no way to get more features when you're rotating the magnetic field. And also, it couldn't be SDH oscillation because the location of this peak doesn't depend on the field you apply. I mean, we go all the way up to 35 Tesla, the peak remains at the same position. And it actually persists to a rather high temperature. And so you can observe this all the way up to, let's say, 90 Kelvin for the first major peak around 0 degree. And what are these angles? And it turns out that these angles are 43.38 degrees and 62 degrees. And they actually corresponding to the real space lattice vector for the B and C direction. So whenever you're whenever you're rotating magnetic field and hitting to the next unit cell, then you see a peak. And then this can also be seen by plotting the angle derivative of your magnetic resistance, and then plotting it as a function of B over C multiplying tangent theta. If this corresponding to this lattice constant, then it should be an integer. And then indeed, you see that in every integer, although we only see 0, 1, 2. Now, this is actually not the first time people have seen this. As Joel pointed out earlier before the talk, people have seen this in this organic 1D system. So it's also a chain-like system, and then even the transport signature looks quite similar, right? You see this distinct peak, and then it's on top of a broad hump. And so there's various way to understand or explain this, and then one of the popular way is to realize that in this quasi-organic 1D system, you actually form some Fermi surface sheets, and then when you apply magnetic field in this geometry, what electrons do is that if you have closed Fermi surface, electrons are circling around a closed orbit. But if you have Fermi surface sheet, then electron will try to traverse a path on the Fermi surface sheet that is perpendicular to the magnetic field and on a constant energy contour. So if you apply to a random angle, then this path will never return to itself. You're going from one Brillouin zone to another and then never return itself. But if you are at this commensurate real space angle, then they will actually form a closed cycle, then coming back to its trajectory. And of course, this is not the only explanation. Phil Anderson has another explanation based on some strongly correlated physics in real space. But no matter what, that's a very different system. So this is the Fermi surface that you kind of expect for this organic. But we're talking about some very small amount of electrons, a tiny Fermi surface that probably occupying just less than 1% of the Brillouin zone volume in the three-dimensional cell. So there's no way all this 1D traverse orbit could apply for this scenario. Instead, we now have a Dirac electrons, high mobility, high magnetic field, that somehow the electrons know something of the underlying lattice. So this definitely reminds you of the case of Hofstadter butterfly of graphene in the boron nitride Maury superlattice. So let's quickly review what's the essential ingredient of a Hofstadter butterfly. So in this Hofstadter butterfly spectrum, you basically have magnetic field, and then this is the ratio of magnetic flux. So when you tune the magnetic field, then you see some repeated pattern when your magnetic flux is 1 flux quantum per unit cell. But and then you have this discrete fractal spectrums as a function of energy and magnetic field. But there's some special magnetic field, which is when the flux to flux quantum ratio is a commensurate ratio, like P over Q, P and Q are integer. Those corresponding to this straight line. That's when your system starts to form some supercell, some mini subbands. So that, for example, like in this 1/2 ratio, you can actually reconstruct your unit cell into 2 unit cell in a 2 unit cell per node. So the new unit cell is twice the size of the original unit cells. And in this case, the new unit cell actually have 1 flux per quantum. And then in this case, it's as if there's no magnetic field applied. So therefore, you reduce to a problem without magnetic field. So people have seen this effect. So Grimes group, they actually see an oscillation associated with this effect. And then the signature is that it only depends on your magnetic field to superlattice flux quantum ratio. It doesn't depend on density. And then whenever you reach this commensurate ratio, then you have a peak in conductance and also this kind of dispersion-like behavior in your whole conductance. So what does this have anything to do with our system, right? This is a 2-dimensional system, and then magnetic field that is strong enough that your flux is going through 1 unit cell is a flux, so that you have about 1 flux per quantum in your unit cell. So actually, right. So in fact, around year 2000, there's a theory paper by Koshino calculating the saturation for a 3-dimensional Hofstadter butterfly, basically a tight binding with a large magnetic field. And then in the condition that when your dispersion along the x direction and y direction and z direction are highly anisotropic, meaning that when you're going along direction, the hopping is much stronger than the other direction, and then it's much stronger in the other direction. Then when you in a fixed magnetic field, when you rotate the angle, you can also create the same Hofstadter butterfly spectrum. And this commensurate fielding actually corresponding now to the commensurate angle, right? So instead of having, let's say, 1/3 of flux quantum per unit cell, now what you need is your flux going through this BA lattice unit cell, and the BC lattice unit cell has this commensurate ratio. So this is exactly the same condition that we have observed this magic angle effect. So let's just quickly go back to this transport signature. And so we see a resistant dip, which corresponding to a conductance peak whenever we hit the commensurate angle. And then this is very similar to the case in the graphene. And then for the whole effect, we also see something roughly similar, but it needs to be resolved better. Yeah. But, okay, this is actually the next slide is my last slide. So yeah. So in conclusion, we have demonstrated strain-tuned topological phase transition, and then you can find out all the details of this work in this publication. And then we also see very strange behavior in the quantum limit as a function of angles. This material. Yeah. Thanks for your attention. This one?
Yeah. So what's the red and light blue line?
So these are magnetic field. So the low field, you see a regular 2-fold magnetic system, right? So you're right that this zero order peaks, right? It's really happening just at the same place where you semi-classically expect the strongest magnetic system.
Yeah. What's interesting is that this light blue one, this dip turns into a peak.
That's right. Yeah, here. Yeah. It's also, though you see a tiny peak on top. Yeah. Yeah, I don't know. I mean, you can, right, like borrow some language from Phil Anderson. You can say that when you apply, so this corresponding to Phil within plane, right? So yeah, so you somehow you kind of disrupt the interlayer coupling and then create a metal insulator transitions between the layer. Yeah, I mean that's I don't know. Yeah, but something along this line. Yes.
So I don't know if everybody agreed with it, but so for the magic angle business, I know that Paul Chaikin was very much in favor of this picture of a so-called lock-in effect, where at those magic angles, what was supposed to be happening is effectively you were getting the formation of sort of 2D layers of conductivity.
Right.
And what that helped them do was to understand, for example, measurements of the Hall effect,
Right.
because what they would see with either the Hall effect or the Nernst effect, as you would go through the magic angle, it would look like you were probing two-dimensional sheets.
Right.
And as the field would go past, you'd see positive to negative Hall coefficient.
Yeah.
Anyways, it's a lot of details. I wonder if that could help you strongly distinguish between that case and then the case that you're seeing, because I don't really see that in your Hall effect. It sounds like you're already convinced that it's Hofstadter, but I wonder if you look into a little bit this lock-in thing, that could maybe also help rule out that it's a traditional effect.
But how, I mean, is there any requirement for this locking happen? I mean, does it generally apply to any one-dimensional?
So in their case, basically the idea was that it was one way of interpreting this magic angle, and it helped them describe all the off-diagonal transport.
Right.
And I think that, anyways, that's just a suggestion.
So
it could be very different.
Initially, we thought something similar of that happens, and then we measured the Hall effect in a very poor geometry. So basically using the longitudinal contact, but just doing anti-symmetrizing, and we saw exactly the same kind of thing that I think what you're referring to, like the Hall effect switching slide near the magic angles.
Oh, you did?
Yeah, but then we do a more proper Hall effect with a proper contact geometry, and then we see something, like this. And then, no, we probably see something on that, but this is actually sitting on top of some very strong background, which is a step-like Hall effect as a function angle. This itself, this step response is also very interesting, which I have no time to talk about, but that kind of complicated story a little bit. But yeah, we're still trying to.
And then why are all the? I think you said it, but I just didn't catch it. So why the temperature scale is so high for this effect?
This might be to do something with similar to the case in graphene, right? They see this all the way up to 300 Kelvin because it doesn't really require to seeing this individual quantized level. It's a band structure effect, right? You're changing the band structure from itinerant band to localized states, right? So it doesn't matter. You don't need a very sharp Fermi energy. You can, going across different energy.
Do you envisage that, maybe photon emission under strain could, shed some light?
Right. Yeah. I think that would be great. Yeah. So definitely remember to put a stem cell in the in the RPS you're proposing or building. Yeah. And we're working with Eli on putting the stem cell on the random beam line, and then we'll see how it goes. I mean, if it works, I think that will apply to many materials, not just the Continental, right?
So you talked in the very beginning about there potentially being some debate about charge density rate in this material.
Right.
Where do you stand on that, and do you see some interest in that?
My stand is that there might be a very subtle structural transition associated with this compound, maybe to do with stacking or anything like that, because there is some reported signature of, let's say, resonant ultrasound on this, but I don't think it's a charge density way. I mean, it just doesn't have the environment to. I mean, it's ultra low carrier density, and there's no nesting. There's nothing remotely close to that. A similar compound, the ZrT3, is a very robust, well-defined compound that Ricardo also studied.
Any further questions? If not, let's thank Jiun-Haw again.